Well, a warm welcome indeed to anyone joining. Thank you for being here. Go ahead and get yourselves a notebook or maybe a notepad, maybe even just some sticky notes. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, the reason why I don't want you to necessarily put this information in with the mass of your notes is because it's kind of like a cheat sheet, nice little trick that I'm showing you here. And it's for memorizing some of these pesky trigonometric identities. If you take a trigonometry or pre-calculus class, you're going to approach a section that is most annoying for lots of students involving trig identities. And once you've been introduced to the different 6 trig functions, sometimes your memory is starting to get stretched a little bit. So there's a way for me to pack many identities into one diagram. This was passed on to me by someone I learned from, a teacher that I learned from. He just kind of smiled and said it was an ancient Chinese secret. I don't know if he was being legitimate about that, but he was a rather serious man, and I believe that it comes from the ancient Chinese. He was Vietnamese and Chinese, I think, in origin, blood wise. So he passed this down. Not many people show this trick or this diagram, but it's a great way of keeping track of so many trig identities. So you're going to just have a big hexagon. Go ahead and draw a hexagon, but don't just draw any hexagon. Let me show you what the hexagon is going to look like. Here is the magic hexagon. And, maybe it's not a perfect hexagon, but I can't draw it that well. Be nice. So you see on this hexagon, I've labeled these vertices, and I've labeled them in a very particular way with a specific order in mind. So I have, starting from this top left sort of section, we have sine, and then going clockwise, we have cosine, cotangent, cosecant, secant, and tangent. And you'll notice that there's a 1 in the middle. They're all kind of connected to the 1. That's going to be important in a moment. So as I've labeled this hexagon, I've repeated it several times because there are different types of identities that we're going to be able to use the same diagram for. The first one, which is the easiest one, is simply the cofunction. Now, what is a cofunction identity? What does that mean? Well, a cofunction, like sine and cosine, as the name kind of suggests, you can see that they're right next to each other, like left to right. And the identity or the relationship between these is that sine of theta equals cosine of 90 minus theta. That's in degrees. Similarly, cosine of theta is related to sine, in this same way. Well, we have 3 pairs of cofunction relations, basically. We have tan and, you guessed it, cotan, and then we have secant and cosecant. So for example, secant of 17 degrees, this would be the same as cosecant of 90 minus 17 degrees. So this would be the same as cosecant of 73 degrees, for example. Okay, so this diagram, make sure that you're putting the correct trig expressions on the correct vertices here. Sine, cosine, cotan, cosecant, secant, tan. Great. Let's move on to the other type of identities that this diagram is useful for, and those are the reciprocal identities. Reciprocal, what does that mean? You guys might remember that refers to fractions, right? Like the reciprocal of A is 1 over A, just flips them. So the way to see these reciprocal identities is to go directly across the hexagon. Look at this. Sine is 1 over cosecant. And similarly, cosecant is 1 over sine. Now you might remember that because that's how it was taught to you. That's how cosecant and secant was introduced in the first place. But did you know that it goes both ways here? Sine is 1 over cosecant, cosecant is 1 over sine, and it doesn't stop there. You can start anywhere you'd like, and if you go across the hexagon, we have, for example, that tan is 1 over cotan, and of course we have that cotan is 1 over tan. Great. And the last reciprocal relationship is between secant and cosecant. Secant and cosine, excuse me. So we have that secant is 1 over cosine, and cosine is 1 over secant. See how that works. Now, the reason why I've written this several times is so that I can use different colors and that it's not going to be incredibly messy. Otherwise, if I draw different shapes and things like that, it's going to get very, very messy. But now, these ones are a little obvious. I probably didn't teach it too much or save you too much trouble. However, now let's take a look at the quotient identities. Now, while we saw that in the previous two types of relationships, you just have to kind of go across. You have a certain starting point, right? We have three distinct relationships here: sine and cosine, tan and cotan, secant, cosecant, as well for the reciprocal identities. Well, the quotient identities, this is where you really see the beauty of this hexagon and how things are arranged. Because the most typical quotient identities that you know of are going to be, or that you'll be told of, are simply that tan is sine over cosine. And that's true. These aren't wrong. And that cotan equals cosine over sine. We know that also from the reciprocal identity. Since cotan is 1 over tan, you can flip it, and that gives you cosine over sine. But did you know that with this hexagon, there are 12 different quotient identities? Holy mama, 12 different identities. Yes, the idea is that the two you know about are sort of illustrated by starting at tangent and saying tangent equals sine divided by cosine. You see how we're kind of going like around the hexagon like this? And that's true, tan is sine over cosine. But the other one, cotan, is equals to cosine over sine. Now, I know that if you're reading it from left to right, it doesn't compute. It's not true. But what I want you to understand is that we can pick the starting point as cotan, and we can go counterclockwise, and that would be a correct quotient order. Cotan equals cosine over sine. But I said there are 12 identities that are quotient identities. That's because the beauty of this setup is you can start anywhere you'd like. Let's start at cotan, and you can go in whichever direction you'd like. You can go counterclockwise, like we did for cosine over sine, or you can go clockwise, which means that cotan is also equal to cosecant over secant. And I can prove that really quickly. This is 1 over sine, and this is 1 over cosine based on the reciprocal identities, which means this is, we're getting into other territory there, which means this is 1 over sine times the reciprocal of 1 over cosine, right? When you divide by a fraction, you multiply by its reciprocal. You flip it and multiply. So this gives us cosine over sine, and we know this is true. Cotan is cosine over sine. I encourage you to try this from any portion that you'd like. You can start anywhere you'd like. Let's start maybe at secant. Secant is equal to tan divided by sine. Isn't that something? So that means secant is sine over cosine divided by sine, which I can just say multiply by 1 over sine. Whenever we divide by something, it doesn't have to be a fraction. Whenever we divide by something, it's the same as multiplying by its reciprocal. Those two would cancel, and so we would end up with 1 over cosine, which we know is secant. So we really start to see the beauty of this diagram, because the quotient identities, there are 12 of them. Like I said, you can start from 6 different starting points, and you can go in 2 different directions from each of those starting points for a total of 12 quotient identities. These are the only ones they're really going to show you in a class. But with the power of this hexagon, we get a little bit more out of it. Now, what's up with the 1? We used the 1 for reciprocals. Is that all the 1 was used for? Of course not. There are also the Pythagorean identities, the most famous of which you'll be taught in class for sure. Sine squared plus cosine squared equals 1. It's called Pythagorean because it's technically like 1 squared, and this is the structure of a squared plus b squared equals c squared. You'd have to look at a unit circle diagram to see what's really going on there. So let's just quickly draw a circle, and let's say that we have any angle, really. We can pick this angle. We know that this is going to be the cosine of theta, and we know that the y value here is going to be the sine of theta, and the unit circle has a radius of 1, which means the hypotenuse of this right triangle is 1, and you can see for yourself, therefore, that sine squared plus cosine squared equals 1. Now, where is that on the diagram? Well, if I sort of highlight these, sort of looks like the nuclear reactor symbol when I do that, but if I highlight these, here's where we really get to see the Pythagorean identities, all 3 of them in action. It's going to be left squared plus right squared equals bottom squared. You see that? So we have these triangles that I've kind of shaded in, and the triangles obviously have 3 angles. They have 3 vertices. Well, the top left is sine, the top right is cosine, and the bottom is 1. So if you just think left squared plus right squared equals bottom squared, you have yourself an identity. The other 2 Pythagorean identities are highlighted in these triangles. So the other 2, what would they be? It would be left squared. So top left is tan squared. And of course there are like thetas or x's in here or whatever. Tan squared theta plus right squared. What's the top right of that triangle? It's the 1, right? So the left squared, the right squared equals the bottom squared. That's secant squared. And then we have this 3rd triangle, which will tell us that left squared, 1 squared, plus cotan squared, that's the right 1 squared, equals to cosecant squared. That's the bottom squared. Of course, you could derive these identities. These 2, you could derive them. Oops. Okay, my text doesn't want to work. These could be derived from sine squared plus cosine squared equals 1. What do I mean derived from? I just mean that if you start with this equation, which we know is true, sine squared plus cosine squared equals 1, if you divide everything by cosine squared, like every single term, then you'll get sine squared over cosine squared plus cos squared over cos squared equals 1 over cos squared. And if we simplify those things, we do just get tangent squared plus 1 equals secant squared. So that's kind of where the derivative, not the derivative, don't want to scare you with calculus stuff. That's where the derivation of these sort of comes from. But the way to memorize it easily is to use this diagram. Now, when you're using these identities, you're not just going to have to simply identify them and that's it. You're going to have to use them and manipulate them, but hopefully this diagram is very useful to get you started on how to keep track of your trigonometric relationships. Okay, that was just a quick little trick. Nice, simple diagram. You can get some experience, practice, make sure that you're writing down this hexagon with the correct trig expressions on each corner. Otherwise, some of these relationships might not work at all, okay? Well, I think that's enough blab out of me. Good luck in your trigonometry class and power through those annoying sections on trig identities and using trig identities. Trust me when I say you're not going to have to memorize all of them for the entirety of your math career, although some of the important ones will show up again in calculus and in Calc 2. I'll see you next time.